Welcome. This is part 17 about the Olshammar engine. It's about exhaust gas recirculation. We present the new design for exhaust gas recirculation. For diesel engines, the improvement is cleaner intake valves, as soot is never mixed with crankcase oil. And for all engines, the improvement is lower pumping losses. And note that this is not limited to the Olshammar engine, but is also useful for other engines. For the Olshammar engine, it needs high turbo boost to be efficient, but with high boost and high temperature we get nitrogen oxides. So the combustion temperature must be low to allow high boost. And exhaust gas recirculation is a solution, but can the standard solution be improved? Here's a standard solution for diesel and LNG diesel engines. It's a high pressure solution. We can see that the exhaust gas is recirculated before the turbo. So we still have a high pressure when it goes through the EGR valve and EGR cooler. And it's still on high pressure when it comes out after the compressor. Problem with this solution is that you have diesel soot in the EGR valve and you have diesel soot in the EGR cooler, and then it gets mixed also with crankcase oil, so it creates deposits on the intake poppet valve, and this valve must be very tightly closed because we have high pressure from the combustion here, so it's very important to keep that valve clean. Here's a standard solution that is used for petrol and liquid natural gas spark ignition engines. And here we have a butterfly valve where we can regulate the intake airflow. And this is used for partial load situations. And there is a good thing about EGR in this case, because when you have EGR circulations, you don't need to close the butterfly valve as much. So you actually get less pumping losses within EGR solutions than without for petrol engines. But you still have a problem with the crankcase oil creating some carbon deposits on the intake valve. And there's still some dirt coming from the exhaust gas regeneration. But petrol and natural gas burns cleaner than diesel, so it's less of a problem. Here's the new design I suggested, and here we have a side port that connects two cylinders. We have two cylinders here that the left one is a combustion phase and the right one is in the intake phase. So when the left cylinder is pushed down by exhaust from the combustion, it opens a side port when it reaches the end before the bottom dead center. And some of the exhaust gas, maybe 25%, goes through the EGR valve, through the EGR cooler, and into the intake from the other cylinder. And in the combustion cylinder, we actually get lower pressure when the piston goes up, so it's less pumping losses when the piston goes up there. And in the other intake cylinder, we can actually get better fill rate because we have the intake air coming in through the poppet valve, but then at the end, close to the bottom dead center for that piston, it opens up this side port and you get the exhaust gas coming in there. So you actually get a better fill rate with less pumping losses. And in the normal EGR solution, you would recirculate through the exhaust poppet valve and then passing an EGR valve and the EGR cooler and then coming in again through the intake poppet valve. And these poppet valves have a lot of pumping losses. So this solution will have lower pumping losses. And if we have a large diesel LNG engine that we know is going to run for continuous operation and at fixed RPM, like a big genset or a big ship engine, and then we know what flow we need between these two cylinders. So we can have an open solution without any valve here, and then we get a very low pumping loss. And it's also possible to use this solution for a low pressure EGR solution. So here we have a petrol engine, inline 2-cylinder, naturally aspirated, often used in motorcycles. And we can see that we can have this solution here, and it can also be air cooled for smaller engines. And here's an additional advantage in this case, because normally when you have a naturally aspirated engine, when you breathe in, it's very hard to fill the cylinder with 100% atmospheric pressure. So you get less than 100% filling rate in the intake. But in this case, we fill it with air in the beginning and through the poppet valve. And when the piston reaches close to the bottom dead center, we open up the side port and we get the EGR gases pushing in with high pressure there. So we get actually more than 100% filling rate in this case. Thank you very much. I hope you found this interesting. And if you have any questions, then please contact me.